Okay, so welcome back to this second part after lunch. So we will now see this second part will be divided into a theoretical one and a practical one. Let's say the theoretical one will be mainly focused on foundation models. You will see now why also fine-tuning. And you will see a bit of, let's say, general information about those foundation models and how they can be used in Earth observation. Then I have prepared for the hands-on part. We have some Google Colab notebooks or general Google notebooks, Python notebooks that can be run on Google Colab. And this will be quite helpful in order if you want to interact a bit with some of the things that I'm going to show you here. Otherwise, if you think that these the foundation models and the coding part behind them might be too challenged, we can always use the previous notebooks on the Eurosat dataset or the one on handling the images, because I would like to give you the possibility to interact with the code, to work with it. I will explain a bit how it works, but it's well commented, and there are a lot of comments made by my colleagues on those codes. So let's see how it goes, and what you prefer based on the background. Also, so in this way, each one can choose its own work. So in this case, I have to thank two of my colleagues, Ruben and Valerio, that I also added as credits to those slides, because they really helped me in solving some, let's say, in preparing this slide, but also the more theoretic, the more hands-on part on benchmarking the foundation models and fine-tuning a foundation model. But let's go into the details. So if you have, oh, why is not going? Stuck. Okay, it seems good. My fault. So okay, this is the overview, the outline of this part of this lesson. We have what are geospatial foundation model, how we obtain a geospatial foundation model, namely what it is, and then we focus on one of the two main aspects, that is benchmarking geospatial foundation models, and then we have some concrete. Here at the bottom, I reported the GitHub repository as in this morning, in which you can find all the codes, and I update also the slides in this afternoon, once the course will be ended. In order so if you want to look them again, they are presented, will be reported on this GitHub code, this GitHub repository. No worry, I can share it. I share also them in case when you make the hands-on part. So let's start with the first point. That is, what are the geospatial foundation models? So let's start, let's say, with a simple overview, and let's thinking about a problem that we want to tackle using AI. So, for example, this is a very important problem because, for example, here we have some input data, so our satellite images, and we want to extract, for example, the biomass, or we want to make an estimation, a forecasting of the biomass. And this is a problem that we usually tackle using satellite images. So one of your colleagues in the previous lesson make a question regarding how many times you train a network from scratch, or what happens if you change the topic, or if you change the, let's say, the application of the task that you want to take on. So what happens that if you want to think about another project, so we have, let's say, some buildings that are in ruins now, and we want to detect the quality of those buildings before and after maybe a catastrophic event. So here is a semantic segmentation task in which we classify also the buildings based on different colors. So this is a task that is different with respect to the biomass that I showed you before. And in this case, in the common, let's say, deep learning pipelines, you should design a model for one task, and then you should design another model for another task. But this is just an example of domains. Obviously, there can be a model that can take all two tasks. But what happens if we add one more? So, for example, we want to detect the crop fields into an image. At the end, this can be also done in a simpler way, maybe. But it depends on the kind of image. So if the image is easy handled, we can also use some filters. But if we need some very detailed patterns, using AI might be quite helpful. Okay, so the solution, in order to have not only multiple tasks, because in this case we can design a neural network, but also multiple inputs. So we have different modalities as input, and we want to use a unique model that is able to take as input different kind of data and give as output what we want, and maybe only one of those output, or all of them, it depends, are the geospatial foundation model. In general, foundation models, we will see now in the details what are you can say their characteristics, but they have to, let's say, respect, let's call it this way, some specific rules. And as I told you before, just the way to handle two different kinds of data, just imagine SAT data and optical data, is quite challenging because they are different, even if they are just numbers. For a neural network, in order to extract such specific information, their data has a different distribution. So, okay, here is just to give you an overview. I'm sorry I was in front of the slide. Those are the, let's say, main principle of this foundation model. So the first, they have to be task agnosticism. So they have to be able to perform multiple tasks. They have to keep the spatiotemporal awareness. So they have to keep the information about mainly the geospatial one, when an image has been captured, and the information about the position, for example, of the satellite. So we are not giving as input only the images, but also some metadata of the satellite, so where the image is located. This can be an additional information that we are always fed into our model. Then we have sensor agnosticism, so they have to be able to take as input multiple sensors, this is the geospatial one. Obviously, this is strictly related to geospatial one. Multimodality, so multiple output and multiple input and multiple output, and adaptability, that is probably the general word, so they have to be adaptable to different kind of tasks. Obviously, and here we come back to the lesson of this morning about the fine-tuning. The idea is that in order to train something like that the first time, it's really, really challenging because we have tons of data, multiple tasks, everything all together into a neural network. And if we want to add one task, how we can do it? We have to train from scratch all the network? No, but thanks to some studies that has been done, we can simply fine-tune this model, the existing one, keeping the previous knowledge, and then fine-tune and add a new task. We will see this thanks to a benchmark that has been developed by my colleague Valerio, that is called Pangea. But let's go step by step. So just some, let's say, general knowledge. Geospatial foundation models are large-scale AI models that are trained on a vast amount of diverse geospatial data, as you've seen before. And then they have to keep this temporal and spatial resolution. So those relationships has to be kept inside of the feature space of the model. So to be more detailed regarding the previous informations, this is what task agnosticism means. So we don't have to be limited to a single task. So we need to generalize regarding the question of this morning, how we can how we can study if a model is able to generalize or not on different tasks. And then we need to enhance the scalability and the efficiency. Why this? Because if our model is a general purpose and we want to add a new task, as I told you before, we are going to improve the efficiency and the scalability because we don't have to retrain from scratch the model, but we just need to use the previous knowledge and add maybe a small data set in order to add a new task to the existing model or to adapt the model to the new task. Okay, spatio-temporal awareness. So in mainly geospatial foundation model, the time and the location are really, really important. Let's imagine that you want to detect a specific building, and if something happens after an earthquake, or for also historical domains, why not? And also, as I said before, they are very important for dynamic applications. Why? Because Earth is changing every day, and we need to have a look at them. And maybe for forecasting applications, that can be any. Okay, more detailed, related to sensor elasticity. So, as I said before, those models, mainly in the geospatial, they have to be able to handle different kind of data based on the different sensors. But a sensor cannot be only, for example, is not only able to capture, for example, some specific information like bands, but some of them, like for example, on the science part of the satellites, they are focused on specific information like altimeter. They focus on ice, on the ice. So they extract some specific features, some specific informations that has to be put all together in order to perform the task on which we are interested, any task, potentially. So in this way, we increase the versatility. Just imagine that you develop an architecture that works very well. Then ESA decided to make a new satellite that uses a different sensor, and you need to make the architecture from scratch. So obviously, thanks to foundation models, you potentially can move the previous knowledge to and all the previous tasks to one domain to another one. Okay, last, if I remember, multimodality. So they have to be able to process multiple types of data. So we have image, text, but also the geolocalization, data point. So in this way, we make, let's say, we enrich our search space, our domain. So we can create many connections, because maybe one satellite extracts a specific information, another one extracts a different information, but thanks to the location, the same information can be put together for every given task on which we are interested. There was also adaptability. Adaptability, as I said before, they can be easily fine-tuned. The objective is to fine-tune easily such kind of models in order to reduce the computation, because as you may imagine, we have just talked about many kind of data, different kind of data, and many domains together that can be performed together by a unique model. So you need to imagine the size of this model. And then we reduce the time needed for retraining from scratch the model. So in this way, we directly connect also to the things that we have seen this morning. Okay, we really like animations. How to develop a geospatial foundation model. So I make a brief recap about neural networks, just to give you an overview, a more detailed one, maybe with respect to the one of this morning that was full of block diagrams. But what happens that here we have one input, our image. In this case, it has, for example, 4 channels. Then we have the weights of the model. I don't know why it is not here. Okay, many animations, too many. Here we have the image. It's divided into 3 channels. In this case, let's consider only the RGB. Here we have the values that goes depending on the kind of the precision of the data that we have. Goes as input to the model. The model has the input layers, the hidden layers that are the layers inside of the neural network, and that can be one, that can be many, and the output layers. The output layers is the one that gives us the prediction. So just to give you, to make a small recap, we have the inputs, the weighted matrix, so that is the weights of the model. That is being multiplied depending on the operation for the features that we give in the input, and these are the bias that are added to our weights. However, okay, just a small recap about the loss function. So our objective is to reach the global minimum. That in this case, obviously, more complex is the problem, more complex is the shape of our, let's say, the convergence behavior. And we want to reach, for example, this global minimum with respect to this one, or another point that can be in this area. To do so, we have the objective function. So we want to reduce, we have the loss function, we have our input, our results, the output. So this is the ground truth, this is the output of the network, and we obtain a value that, for example, can be 2.4. that is the current one, that is this one, that is still a local minimum, but not, for example, the optimal one that can be on the left side. So we perform the training in order to obtain a convergence of our model. Regarding foundation models, this work that is proposed for neural language models, so many systems, AI models that work with text, said that higher is the amount of, maybe simple, but the concept is that higher is the amount of information that your network can process, higher is the number of data set, obviously higher is the computational complexity, and better are the results that you can obtain. That is simple from this way. The bigger, the better. However, labeled data, as said before, is quite expensive. Because here, this is this image extracted by this work, you can see how the time that you need to spend, that you need to allocate when you design an AI pipeline. So you have, for example, data labeling, data cleaning, the data aggregation, the identification of the data that you want, and the data augmentation strategies, for example. And then, as you can see, the training part and the optimization is just the smallest one, because better are the data that you fed into the neural network, better is the better, and faster, better it will perform, and faster it will converge. So, still a bit of expertise, you still need to have it. Okay, so this is also a data set that has been released by ESA. It's called MeasureTom, and it collects embedding, so data that are embedded from many satellites. So these are petabytes. So you can see the amount of data that are inside of this data set that can be used for this kind of applications, any kind of application, because here you have Sentinel-1, Sentinel-2, Sentinel-3, Sentinel-5P. So you have many missions from which you can extract data. This can be helpful for applications, can be helpful for tasks, specific tasks, and they always come from the Copernicus mission. So as you may imagine, process like many petabytes of data without AI can be quite difficult. If you do the same with an AI model and you want to feed all those data into an AI model, again, it's still difficult, a bit less than making by hand, but it's challenging. So, in order to do so and to level one of, let's say, the main characteristics, let's call it in this way, of foundation models is how they are trained. So they are trained because obviously you may imagine that that big amount of data has to be labeled, and label in most of the cases has to be put manually. So we use a strategy that is called, this is always, let's say, knowledge on foundation models, is called self-supervised learning. So what happens? In the supervised learning, like in the, what's called on the Eurosat dataset, on the code that I give you, you know you have the images, you have the labels, because the images has been labeled. So at the end, you know almost everything, and you just need to design a model to train that has to learn the labels based on the image. Here, or you have the unsupervised, as I show you always in the previous part, in which in the unsupervised, just to give you more details, you have the images, but you don't have the labels. And you want to learn the representation of the data. So what does it mean? You want to use your neural network to distribute the information in the search space, in the feature space of the model, in order to, let's say, group them into big clusters. This can be a point of view. However, in this case, we use self-supervised learning. So what does it mean? It's neither supervised, neither unsupervised. It's a trade-off between them. So what happens? We don't have the labels for the pre-training. So what happens? We have some images, we want to learn their representation in the pretext task. So we want to represent, we want to understand how the features inside of the image are distributed into the feature space of the neural network. Imagine that like the feature space, like the knowledge, no, it's not right. Like the biggest area of the biggest informations that the model has. Let's call it in this way. And then we try to move the representation that the architecture automatically learns, thanks from some unlabeled images, to learn. So we fine-tune the big model on an existing task on which we have the labels. So what happens? As before, we fine-tune a model. But what is the things that we leverage in this case? The knowledge of the model, not in performing a task, but in dividing the distribution of the features, so of the information that the model has into, let's say, its knowledge, in order to improve the performance on a second task that we usually call a downstream task. I know that might be a bit complex, sometimes also for me at the beginning. In this case, first, why this is important? First, because to train a neural network, we usually need a big amount of data. This big amount of data has to be labeled, and it takes time. So in this way, we pre-train a model on a pretext task, and then we might fine-tune on a small data set. So we can reduce the amount of data that we have to collect. That might be challenging for different applications, and then that we have to label. In this way, we leverage the previous knowledge to this second task. That case is this one reported here. Here I would like to report some examples that might be, now we have many examples, that might be very simple at the beginning, but they have many applications in the real world. So let's imagine the task in which we rotate an image. So we just rotate an image. This task of rotation can be learned with a Cartesian coordination, and we are going to distribute, for example, imagine instead of rotation, let's just imagine the flip of the image. So we want to see if an image is on one side or on the other. We can distribute this knowledge, the internal knowledge of the network, better. We can give to the network this information in order to learn this kind of distribution. Okay? So in this case, you have the image in a way, and in the other one, you have in a different one. Why this is important? Because you can use this information to an additional task that can be, for example, I don't know, you want to detect if you are capturing an image in the wrong way with your camera, because, I don't know, it's placed on a drone and it might be a problem. Thanks to this task, we can simply move the knowledge of that from the pretext task, that is just this rotated example, to a practical problem in which you have maybe few labeled data and few samples. Okay, we also have a bit of math. So in this case, we have a big set of unlabeled data. We want to learn our downstream task. So we want to collect, for example, okay, the target pages, so X and X. So our model has to learn, given the input, obtain a specific output, given the transformation that we give as output. Let's go to let's say maybe something that is more practical problem. Okay, which is our goal. We want to obtain a strong model representation from a large data set. So we have a lot of data that are labeled, and we want to represent it. We want to obtain this representation into the feature space. Then we want to improve in a supervised way. So thanks to the dataset, before, a downstream model. Okay, on a small dataset. And this is the standard formulation. Okay. Oh, 2 minutes. Okay. Okay, this slide is the different input modalities. Why this? Because imagine, for example, that we have a drone, we have an airplane, we have a satellite, and what happens? That they capture the same data, maybe the data localized in the same way, but from different perspectives, from different views, and also in different times, March, June, July. This made it a bit challenging because we want to put everything together. Why? Also because this can be really important when you put all the information together, because you may find some specific patterns that are hidden into some behaviors that we may not know. So, for example, a specific kind of wind together with a flood, increase of flood, that might lead to some specific behavior of the Earth. And you can collect those information. Oh, why we have this? Okay. I don't remember why this is fine. As said before, this is just a recap of all the input modalities that we have thanks to the different satellites. Oh, too many slides. Okay. In order to perform this task, oh, there are all those layers. Okay. Okay, in order to perform this task and design the network, like I want to learn this representation of the rotation, just imagine, we have to design a neural network. At the previous one, in the previous lesson, I show you that the two main, let's say, layers are the convolution one and the self-attention, like vision transformers. However, maybe there are more complex tasks that we are going to face with foundation models, like you want to predict something in the future and you want to keep in memory, or you want to know what happens at time 0 and at T1 in order to predict the T2. So we want to keep some previous knowledge, and just to give you an idea, we use this recurrent structure. This can be done also obviously for text in order to understand and predict, let's say, the next word based on the semantic knowledge that we have before. This is just an overview, just a slide to give you an overview of different kind of layers, also the causal attention. So it's, let's say, randomly connected. You reduce the number of connections you usually have in the self-attention. And this is quite helpful in some situations because this input is connected only to the next ones and not with all of them. And this obviously reduces the computation. Each connection is a weight. But why this is important? Because coming back to the rotation problem, we want to learn a rotation pattern, but that we don't know on our labeled data, but we might know on a pretext task. So for example, we can have an image of a bird, we can apply a rotation, that is a specific rotation, and then we can apply this rotation, and we want to give to our model, we want to give to our model that is placed here the ability to learn which kind of rotation, or better, to generate the image based on the rotation. An image that the system had never seen. So, just to use a bit of math, we have our learning model, we have the transformation that we want to learn, our output will be the angle, in this case, and we have the design that is the angle, the angle and its rotation that is applied here. As you can see here, rotation is represented as classes, so 0, 1, 2, instead of values, but at the end is the same. So what happens? They use, for example, focusing on this model, they then create a model in order to predict, maybe this is a unique model, I don't remember exactly. However, they use this model, the convex, in order to predict if an image is rotated and which kind of rotation has been applied. To do so, they apply the argmax of the prediction of the model, and based on the maximum probability, you obtain your desired output. Why this is important? Because if you perform this task using a standard supervised strategy, this is the behavior that you obtain on the best accuracy after many examples. While in the semi-supervised, you start just at the beginning obtaining closer results with respect to the best one. However, why this is important? Because thanks to this strategy, even after few samples training, you can still have very good results. moving to the standard pretext task to the downstream one. But why this is important? This task is important. Let's move to a geolocalization task that is closer to VO. So, for example, in this task, you don't have the rotation value, but you have the geolocalization, the information of latitude and longitude. And we have two images that has been captured in a different time. Obviously, a system is not able to tell you, yes, they are two images or not. Maybe, yes, you have to have a look of them. And if you want to see maybe if there are some, if there are some, let's say, missing parts, something happens in the meanwhile. And in order to do so, you can feed this information into your model, and then you can leverage this one that is a loss function that is called contrastive loss. What does the contrastive loss mean? The contrastive loss tries to close the gap between images that comes from, let's say, that are equal. In this way, a model learns that the image is invariant, let's say, better learns how to detect if the input that you give, the two inputs, are the same or not, independently, based on the kind of, independently from the temporal perspective. And this is quite important if, for example, you are doing some analysis from satellite images and you are capturing information from different weather. Otherwise, you need to wait for the next one, just to give an example. Why this is important? Because we are now going into the concept of contrastive learning. What happens in contrastive learning? We have a model. Okay, we want to learn this model. We apply a transformation. So we are now going close to, let's say, the most complex part that we'll see later that is related to generative AI. We want to learn the model, and we want to understand if a sensor, if the image comes from the same family, okay, or not. So why this is important? First, for foundation models and self-supervised learning, but also because, for example, this image is rotated. So again, you can keep the previous information of the rotations, and then you can add the contrastive loss. So what happens? In contrastive loss, you are making images that are equal or comes from the same family. Let's imagine that is not a bird, but it comes from the same class. So you have the river, the highway, as I showed you before, and you want to attract them. Or you want to repel the ones that comes from different, let's say, from different classes. Why this? Because in this way, you are going to define your search space, your feature space. You are going to increase the distance and make it closer from the same class. Why this is a very, very good solution? Because it has been used in this paper that is quite famous, CLIP. I don't know if you have ever used text and image together, but they design this model that extracts features from the image and extracts features from the text, and then try to connect them, image and text, based on the set of image that you give as input. So what happens to go into the details? So we give as image, we give as input multiple couples of text and images based on assumption. The assumption is that we know that in the set of image that we give to the model, most of them are correct. So the text represent the image that is given as input. Based on this knowledge and then the contrastive loss, the model, without any labels on the image, has to try to connect text and image together and learn the relations between them. Why this? Because at the end, they design this table okay, based on the input images and the input text that you give. And the model wants to learn to maximize, like in a diffusion matrix, this diagonal. This is really important because that's true. You have the label, you have the images, but in this way, after training many times this solution, you can use, let's say, the one that is called zero-shot prediction. So what happens? You give as input, for example, a data set, you give as input an image, and automatically, using the previous knowledge, you can obtain, for example, the text that describes that image. That's really cool. It's a very good work that I made. And also very challenging because at the end they based on this assumption during the learning procedure. And thanks to the contrastive loss that try to put, let's say, the features that comes from same classes together and to repel the others. Like in this way, maximize this diagonal and minimize minimize this diagonal and maximize the distance with the others. Why this is very important, the clip one, because the same features is also used in geospatial models. For example, we want to understand if two images comes from the same, or in this case, two tiles of the image, comes from the same area. Again, how we can do this? Thanks to the contrastive loss. So we can try to close together features that comes from have a similar distribution and comes from the same classes, and try to repel the others. Here you have some examples. They also, in this case, design an architecture, and they compare different architectures. But just to give you an overview of how these can be used, and why this is quite important into the foundation. Okay. The same clip strategy and algorithm is also used for satellite images. Into domains, we have the pre-training, and then we have the downstream task. So again, we have the pre-text, and then we have the downstream task, on which maybe we have a few labels. So in the pre-training, we have images, in this case, and we have some samples, some locations. We want to encode the image, we want to encode the location, and then we learn the connection between images and locations thanks to the contrastive learning objective. So in this way, we are going to learn those kind of patterns. After that, we move to the downstream task. In the downstream task, obviously, here, the amount of samples that are labeled is very limited with respect to the entire data set that we fed, because we based on this assumption that most of the images are correct and labeled, but not all of them. Then we move to the downstream task. In the downstream task, for example, we have in this case, we have we want to detect the location, so we use the location encoder. We apply, for example, a downstream objective that can be, we can also generate the image if you want, giving the label as input. Or, in the opposite way, we can take an image and try to detect, for example, from which location it arrives. Or, additionally, if we have a specific domain, a specific task on which we have our images, and the sum of those information can be helpful for our downstream task, we can leverage the previous knowledge that is used for CLIP for any general downstream task that you're trying to face. Okay, let's now move to the reconstruction problem. This is quite important, mainly in remote sensing. What does it mean, a reconstruction problem? In the reconstruction problem, again, you want to reconstruct an image, but maybe you don't have a data set that is designed for, or here we are going back to the, let's say, closer to the generative AI, it's not closest, it's generative AI. What happens? We are going to give as input an image, we are going to encode the information, and then we are going to decode. What does it mean, decode? We want to reconstruct the input. You may say, okay, but this has no sense. No, yes, because in this case, we are going to reconstruct the input based on the missing information. This is the general task. So again, for example, just to give an idea, this is the input that we have, this is our ground truth, and our model has to learn how to reconstruct this. Why this task can be quite important? Because you can imagine what happens with satellite images. So on satellite images, this generative AI pipeline is quite important. Because it might happen that, for example, you want to reconstruct an image of an airplane, an airport, whatever it is, but you don't have, let's say, the needed information. Obviously, at training time, we can mask the input in order to train our model. But maybe there is some clouds on top of them, and you don't know what happens under the clouds, or you want to at least try to reconstruct them. So in this work, sorry, too much. Okay, so in this work, they try to collect many information for the reconstruction in order to keep some of the features of foundation models. However, and here is probably one of the most important works that we have done regarding the foundation models and generative AI. This one is called TerraMind. It is a work that has been developed by ESA and IBM and other important companies in order to handle multiple modalities. So we have this tokenizer in order to compress also the text and different level of information, not only the images at different levels, but also we use this encoder and the decoder, where it is, and the decoder in order to reconstruct an image. So what does it mean? I give a model as input. Let's imagine a satellite image with a bit of text, and I want to modify that image. But pay attention, I don't want to modify the image. I want to modify the content of an image based on a specific information of the text. In order to do so, I have to leverage all the previous knowledge, like the one used on Clip, at least the same similar ideas, the similar ideas, and I want to generate something new. Let's imagine that this can be helpful in order to understand what happens if I decide to remove a forest. Okay, I have a forest, I decide to remove and create some buildings, but how this can affect, for example, the biomass, how this can affect the flows, everything that is around the image. This is mainly to make simulations, obviously. So we now move to the generative models. So just to give you an overview, okay, on text, generative models aims to understand, let's say, the probability to have a specific, in this kind of example, we have text. So which is the most suitable text after the sentence based on the previous knowledge. We can skip all the complex mathematics because we have a picture, this one, that easily not, but clearly gives an idea of what happens. So we have our initial state, it is noise, we don't know. And then we move in the forward process, goes up to our, let's say, desired output. So we learn how create from the noise the desired output. Then we have the backward phase. So we learn how to, let's say, not correctly destroy, but how to go from the desired output to the noise. And then we change the noise distribution in order to obtain from the output the desired input. This is the common process. So, so in the forward process, we start with the image and we go to the Gaussian noise, and then we have the wrong way. But we start from the original one, and then we go from the time t. Yes, correct. I said the times are the opposite way, and then we come back in the reverse phase. Sorry, wrong time steps. So in this way, our model modifies the noise and learns how to go from this information to the last one. Why this? Because when we give as input, for example, an additional token, or imagine the text together with this, thanks only to the text that we add, so we condition the diffusion model thanks to the text plus the noise that we have trained give us a given output. Okay, maybe I made it too simple. That might be. Okay, regarding generative models and foundation models, the main issue that we face with TerraMind is that we are stuck from the kind of input that we have to use. So what does it mean? That TerraMind works well, but we need to give to the model some specific inputs. So like Sentinel-1, Sentinel-2 data. And what happens if one of those data are not available? In this work, that always carried out with one of our visiting researchers, we try to create this autoencoder that is based on tokens. So the autoencoders that, as before, compress the data and then recreate and to encoder-decoder process, is able to leverage only some specific tokens that comes from the different images, the different inputs, in order to modify that specific image, as in a general way. This is the encoding, then we have the decoding phase, and during the procedure, we generate only the image, the sample on which we are interested. The other will be noise. Why this? And what is the novelty introduced here? We leverage the use of vision transformers instead of convolutions. Vision transformers use those tokens, and some of them can be easily put equal to 0 in order to avoid to use all the needed inputs to our model. Unfortunately, previous models are always stacked by a specific set of inputs. Okay. Okay, for example, here we have some images, and then we condition them in order to generate the altimetry map. And this is the real, and this is the generated one. As you can see, we have those data to train the model, but the obtained one, at the end, the generated one, are quite close to the real one. Imagine that you can do this. You can generate data from any kind, from any point of the world without ground truth, but to train, at least in the downstream task, you still need some real data. Okay, just an overview. This image, this model is able to generate images in different, let's say, multiple images at the same time. Just to give you an overview of, for example, here I've reported some small and finer details. But for example, here this is the ground truth created the lake. If I remember, this change makes the springtime, so it changed the weather. So it's still a good model that can be leveraged for many applications. Okay, we can now move to the future. So some products that are extracted has to be kept in mind, mainly when you are interested in spatial and time, want to connect space and time together. This is quite challenging because spatial resolution is going to increase depending on the satellite and then on the missions. And also the time steps of the data are quite important. So when the data are being captured. Obviously, you need to reconstruct them if you want, or maybe it can be helpful to reconstruct and try to recover them. Obviously, this maybe will be challenging, but at least the Sentinel-2 can be done. So also move from one satellite data to another one can be really a promising research direction, at least for us. Okay, last few points. Benchmarking geospatial foundation models. So this is just to give you an overview of the amount of geospatial foundation model that exists nowadays. As you may imagine, they are too many. And you need to choose one. Okay, this is Valerio's slides. So let's benchmark them and find which is the best. So this is very important because first we need to perform the evaluation of the model, and then we need to see if the model behaves well and is robust to different applications and different domains, and also study maybe which can be the improvements that we can apply on them. So this is just an image to give you an idea of the dataset that is composed that are inside of Pangea. So Pangea is a dataset, a benchmarking dataset that is composed by multiple different kind of input and multiple tasks all together, and has been designed to benchmark such kind of foundation models. In the hands-on part, I have a Python notebook on which you have this Pangea. You download it. You're not downloading that dataset, but you can simply add a new dataset or a new task or a new neural network into the Pangea dataset. Why this? Because you can leverage into Pangea also some models, some pre-trained models that can be easily used to tackle the specific task. So if you want to change and add a new dataset for the specific task, you can leverage the architectures and the task that exist. This is the amount of products that we have inside of Pangea, so many, and for many different kind of applications. Most of them are semantic segmentation, but it's been also increased for classification tasks, just because semantic segmentation is, let's say, is a classification with steroids, because we classify each single input based on the classes. And these are the data that are inside of Pangea, and as you can see, are widespread. Try to be widespread all over the world, mainly this data, not mainly in the US, based on the data that we have available. Those are the geospatial foundation of the pre-training data set, and not geospatial, yeah, exactly. Those are the models that have been used inside of Pangea. And as you can see, some of those models, even if they are called as foundation models, most of them, they are pre-trained and trained only on specific kind of images. However, still a very large volume. Then we perform an evaluation of those models, and we compare with a very simple model that is the UNet. The UNet model is designed for medical applications. And what happens? That, just to give you an overview, the UNet baseline, that is a very simple model, when you want to design a model to tackle a specific task, it performs slightly better with respect to specific foundation model pre-trained that has been pre-trained and just tested on different domains. So what does it mean? This highlights the fact that let's say, not all the foundation models are just ready to use. Also because they have limited amount, so it's just a way to give you the idea that it's still a research domain, because some of those models, when tested, for example, on a different specific data set, and with respect to the kind of data on which they are trained, obtain slightly better and slightly worse performance than a network trained from scratch. Except for one, that is Chroma. Chroma works quite well, for example, but it depends, it's good balance. And mainly, we note that there is this, let's say, quite logic, but important correlation. So the best model, for example, here, Chroma, that performs very well on Sentinel-1 and Sentinel-2 data, that is the best one. It works very well, but just because Chroma is trained on pretext tasks that are Sentinel-1 and Sentinel-2 data. So obviously, but not so obvious, we found this kind of correlation between the kind of data on which the model is trained and their performances. So what does it mean? That we still have to work on the generalization on the different modalities of those models, on the different modalities, on the kind of. As you will notice, you will see that similar performance comes also for remote clip that are trained on this specific class. However, we also study what happens when we reduce the labels to such kind of models, and we still note, I don't remember if there is, sorry, and we can still note that if we reduce the amount of labels, okay, the unit and the division transformers in general perform quite good, but still Chroma keeps some very good performances when we reduce the amount of labeled sample that we give it. So let's say that except for Terramine, that was not ready when Pangea has been developed, Chroma was a good starting point for foundation models. But as said before, it's still something that can be, let's say, researched. Last, I would like to give you this. This is the GitHub repository of Pangea. It's an open source, and you can collaborate with them. There are many contributors to a dataset, a network, and play with it. I have the code also for later. Those are some nice achievements from this part of Terramine and foundation models. Okay, so some final remarks. Always Valerio is super happy about this. So it's very big. It's something that is very cool because we can potentially do many things thanks to these foundation models. But as I told you, it's still a research, let's say, point, and maybe for application it depends. However, it's very important also to benchmark them in order to determine their performances on different domains, on different tasks, and also they are our staff are, let's say, ESA staff are also open source projects, so you can easily interact with them and try to improve. So there should be. Okay, I prepared this small set of slides just to give you an overview of the ESA PhilLab. Those that I show you are just some of our researchers, mainly the Terramine and the other model. But I've seen that, let's say, some of you might be interested in getting in touch or collaborate with us. So this slide I showed you also before. So the idea of our lab is to extract information from satellites, leverage the AI and innovative and disruptive technologies to get inside. So as I told you before, goes from the Earth observation to the Earth action. I show you this. I just showed this slide. However, we would like to bridge the gap between, let's say, and interconnect universities and industries in order to speed up this, the process of this involvement of disruptive technologies and the three axes that I showed you before. So I'm not going to the details. But there are some few slides. Exactly. Okay, we have two main ways of collaboration that I quite skipped before. We collaborate throughout visiting professors, research fellows, PhD, but also visiting researchers. So if you come from a company, we host also some colleagues that works on satellite images on other companies, and we spend a bit of time together in order to collaborate on common interests on topics, obviously a common good. And also, if you are more related to apply for funding, we also have an Incubed program for startups, and the invitation to tender created by PhilLab. I don't know if this still is open, but it's just closed, but there will be 2 times per year, so we will have many of them. Just to propose, for example, application ideas that can be funded by the company. Obviously, if you are curious about this, okay. Oh, too many slides. Okay. Just coming back to this slide, in order to get in touch with the PhilLab, you can or contact some of us if you get in touch with, or we have the Collaborative Innovation Network, that is a system with which we, let's say, have an overview of all the possible collaboration and try to manage all of them, also for visiting researchers or whatever. And if you want a bit more details, don't miss the session of the BIT conference of the 2nd of October, in which there will be people that are more focused on these, let's say, aspects, mainly from the Explore office and the Invest office that we have inside of the PhilHub, to give you an overview of how you can, let's say, collaborate with us and work with us. So if you have questions for this part, I will be more than happy to answer. I know that the concept was quite complex. Otherwise, we can go to the hands-on part. Questions? Something to do?